Good day for everyone. We are Stephanny Frasser, Manuela Lopez, and Paz Galindo, and we're going to present you our practice 4, which name is Conductivity in Composite Materials. We are going to begin with a brief introduction. To start this section of the report, we consider relevant to mention what thermal conductivity is. Basically, it is a mechanism of heat transfer on an atomic scale that occurs by the collision of higher energy molecules with lower energy molecules. This measure quantifies the ability of a material to transmit thermal energy when a temperature difference occurs between regions. It is usually calculated using Fourier's law, whose equation is presented in the slide. The importance of thermal conductivity lies in the fact that it is useful to choose a suitable material to obtain efficient heat transfers, to select materials properly in the case of using heat exchangers or reactors, to have a criteria when developing a material with a specific thermal objective, and to improve the efficiency in equipment involving thermal energy. Now, continuing with the transport of energy at the molecular scale, there are two types of energy carriers that can be distinguished: electrons and phonons. Electrons are particles that transport thermal energy as they move through the structure of atom in metallic materials and move in the direction of decreasing concentration. Phonons are present in non-metallic materials such as semiconductors and are elastic wave package that propagate in a solid and carry thermal energy. On the other hand, the thermal conductivity of solids is influenced by different phonon or electron scattering mechanisms, which limit the transport of thermal energy. Some of the scattering mechanisms that influence the thermal conductivity of solids include phonon-phonon interactions, phonon scattering by bond defects, gain boundaries dislocation, phonon-phonon interactions, and phonon-electron interactions. Another important factor that can affect thermal conductivity is anisotropy. This is a property of materials whereby physical properties such as thermal conductivity vary depending on the direction in which they are examined. Anisotropic materials have different thermal conductivity values depending on the direction in which they conduct heat due to how their structure is shaped. In these cases, heat will flow more rapidly in a certain direction because of how the structure is formed. One example of this type of materials is graphite, that is one of the materials that are tested in this practice. Now, we are going to continue with the objective of this practice, which is develop a protocol to determine the difference between a pure material and a composite material.
The methodology we proposed consisted of having a constant heat source to which one end of the material was attached. Subsequently, the temperature was taken every certain time at a certain points of the material. A difference with the methodology used in the laboratory is the simplifications that allow us to arrive at the equation used to calculate the conductivity. In the laboratory, a methodology very similar to the one we proposed was used. In this one, a plate was heated to 120 degrees Celsius and 8 centimeter pieces of each material were cut. The material was taped to the plate and it was determined that the temperature will be taken every 2 centimeters every 2 minutes until reaching 6 minutes. With respect to the ease of data collection, this was not very simple with the laboratory equipment, which leads to possible errors in temperature measurement. There were major problems, particularly with the fiber that had polypropylene, as it melted quickly on contact with the plate, generating cuts in the fiber that can affect the heat flow. One way to make data collection easier could be to cut a longer length of the filament to make it easier to collect while using the thermometer to collect data. For the calculation, it is assumed that the heat flow is in one direction only, in the x-axis. Also, being a solid, there is no velocity associated with a fluid, so the substantial derivative is simplified.
Once the procedure was carried out, we obtained timed results for each type of material. The tables show the results for rice and copper fiber. The measurements were made every 2 minutes for 6 minutes at five different distances on the wire. Here you can see the results for graphite and cocoa. In general, a common trend is observed where the more distance from the heat source, the lower the temperature is, and also the more time elapsed, the temperature of each section increases.
For the calculation of the conductivity, the equation presented here was used. This results from the simplifications presented in the methodology. To find the second derivative value, a simplification was made which results in a square feet graph for temperature versus distance. While for the derivative of the temperature versus time, these variables were plotted for each point where the measurement was made, and the slope corresponds to the value of the derivative at that point. Being an anisotropic material, a conductivity is obtained for each point where the measurement was made. The graph obtained and the data used and conductivity values obtained for each material are presented below. Here we can see the propylene with cocoa, and next we're going to see pelea with rice husk, pelea with graphite, and finally copper.
It is observed that in all fibers the temperature is increasing in each region proportionally to time. Additionally, it is determined that the one that provides the greatest heat transfer is the rice husk filament with PLA, since it is the one that has the greatest temperature change. Then the graphite with PLA, and the one with the lowest slope is cocoa with polypropylene. The results are consistent with those consulted in the literature, since organic materials have high porosity due to their less dense and organized nature, which cause them to have low conductivity. These organic materials contain structures similar to cellulose. It is characterized by having intermolecular space, pore, between its layers, which make it less conductive than, for example, copper or isolate polymers. What can affect the conductivity of each material is the fiber matrix interface. The porosity of a material is what determines its conductivity, since the greater the intermolecular space, the less is the molecules will have to interact, and therefore the less heat transfer there will be, since there will be fewer collisions between molecules. For the design of a structure for an ice cream parlor with an isolating layer to preserve the internal temperature, which must be -4 Celsius, the use of aerogel is proposed because it is a great thermal insulator. It has a low conductivity, approximately 0.016, and it is very light. Additionally, it is highly porous, so it can trap gases and liquids inside, and it is very rigid. When designing a heat exchanger to increase the temperature of a mixture of acetone and nitrogen, it must be taken into account that it should not exceed the temperatures at which acetone boils. Therefore, the use of polyethylene is proposed because it is resistant to low temperature, tensile stress, and abrasion. Additionally, it has moderate thermal conductivity so that the acetone does not boil but gets hot enough for it to enter the flash separator. If the substance is anisotropic, Fourier's law is like this. Where kappa is tensor, its conductivity varies with respect to the type of flux that is transported and the direction in which it's transported. For example, it depends on whether the X component of the heat flux is transported in the x direction, kappa xx. If we take energy equation, change equation, simplifying the enthalpy, we assume V equals zero, an incompressible substance like these equations. Using the equation in the appendix A of BSL, we have an equation like this. Since we only took into account the heat flux in the x direction, and since kappa only varies in x, otherwise it would be impossible to calculate with the data, the equation is like this. Since kappa the xx does not vary with x, since it is the same direction of flow at transport, the equation is like this. If we take the derivative with time and the second derivative with respect to x at any combination of points, we will find a kappa xx. The data does not allow us to extract more components of the tensor. If all the combinations of x calculated are different, it is due to the experimental error since only one component of the kappa tensor is calculated. If we wanted to calculate the others, we would have to calculate other flux direction in the fiber and or another coordinate axis. For example, the variation in the conductivity of this fiber is due to the fact that we assumed that 100, 120 was the temperature at the edge of the filament, but it was actually of the heating plate. And if you look closely, the other values are very similar.
In conclusion, we were able to achieve the objective of develop a protocol to determine the difference between a pure material and a composite material. Additionally, we determined that the best insulator is the mixture of cocoa and pelea because it's the one that took the longest to transfer heat and has a hollow structure. Conductivity varies depending on the molecular structure of each material, and materials with high porosity are bad thermal conductors.